Hi everyone, this is Paula again. This is Toolkit 2-6 on plugging values into a formula. We're going to get more comfortable using formulas, but we're also going to be learning about order of operations and some calculator skills. Lots of quantities are related to each other, and what we're looking at here is the relationship where one quantity depends on another. For example, the balance of a bank account is related to how many days or months have passed. We wrote formulas like that in our 2-2 linear models activity. We could say the height of a plant is related to the amount of fertilizer used. Sometimes quantities have a predictable relationship, like the relationship between degrees Fahrenheit and degrees Celsius. When a relationship between quantities is predictable, we can write a formula to describe the relationship. So we're going to be looking at formulas, and then we're going to be using them and getting a little more comfortable with letting letters represent different quantities in a formula. If, let's say, your bank balance is represented by A equals 850 minus 50t. Identify the quantities in each and which letter you think is used for each of the quantities. When I look at this, I see this 850 as the starting balance, and the minus 50 meaning that the balance drops $50 every month. But interestingly here, when they're talking about the quantities, they're talking about the A, which represents your bank balance. A changing bank balance is dependent on how much time has gone by. And the balance also depends on these numbers, of course, but the variables are of interest because they can both change. So if I plugged 5 in here, I'd get one balance. If I plugged 10 in here, I'd get a different balance. How much money will be in the account in 8 months? Well, 8 needs to be substituted right here. So then we do 50 times 8, or 8 times 50, and get 400. And the 400 is how much money you've lost in 8 months. So then you take 850 minus 400 and find that the new bank balance will be 450. Notice that we multiplied before we subtracted, even though reading this left to right, it looks like subtraction should come first. So we'll delve more into the order of operations. Here's a different formula. When you travel outside Oregon, most places have a sales tax. The total cost of what you buy is related to the tax rate as a decimal and the pre-tax price of the items you're buying. So I'm giving you some hints up here about what these letters could represent. Let's list all the letters in the formula and then say what each represents. The C, the T, and the P. So C represents the total cost. That would be the cost at the end after you've included the tax. The T represents the tax rate as a decimal. This formula won't work unless you convert the tax rate as a decimal. So for example, 8% sales tax would have T equals 0.08. Okay, and then P is the pre-tax price of the items. So what would the total cost be if the sales tax is 9%, 0.09, and the pre-tax price of the items you are buying is $50? I'm going to write down this formula. And then I'm going to insert the values that I know. I know that this is 0.09 and this is $50. Okay, so I'm going to have 1 plus 0.09 parentheses closed times 50. Now here, what should I do first? Order of operations is going to tell me to do parentheses first, or the operations in parentheses. So I'm going to add those up. 1.09 times 50. And then when I multiply those, I get $54.50. If your calculator says 54.5, please add an extra zero and put a dollar sign on your answer, because this is a money answer. Now, some people might have had the impulse to simply do 0.09 times 50. If you do that, you get 450, and that's the tax amount. And then you can do $50, which is your pre-tax price, plus 450, and then you can get the total including tax. If you were thinking of doing that, that's also a perfectly acceptable way. But this way is a little bit of a shortcut, because well, maybe they're both the same. Multiply and then add, versus here we added and then multiplied. So this is the one that uses the formula way. This might be an intuitive approach. I'm honestly okay with both of them. But on the rest of this activity, we're going to try to use the formulas that are given to us, because they might be more complicated than we can just predict on our own. Here's a relationship that you may not have seen before. The total cost in cents for running an electrical device can be found if you know the number of watts for the device, the amount of time you're using the device, the cost of your electricity, which is in cents for each kilowatt hour, and then we use this formula. Identify the quantities in the formula and which letter is used for each quantity. C, W, T, lowercase c, this was an uppercase C, and then we divide by 1,000, so we don't need to say what that is. So this big C is going to be the total cost of electricity for a device. And that, when we get that answer, it's going to be in cents. That's what we were told. W is equal to the number of watts for the device. Sometimes you can look at the back of an appliance and see how many watts it uses. T is equal to time in hours. And C is the cost of electricity per kilowatt hour. This is something that you might be able to see on your electric bill. Okay. Yes, and this was also in cents, because it said cents for each kilowatt hour. So what is the total cost of charging your phone if you have a 12-watt charger? Okay, that tells me that W is 12. It takes an hour to fully charge. T is equal to 1. And the cost of your electricity is 8 cents for each kilowatt hour. So that's my lowercase c, and that's 8 cents. Notice that because this asked for the value in cents, I would not put 0.08. That would be a dollar amount. I just put down 8 because it's 8 cents per kilowatt hour. Okay. The unit here is watts. The unit here is 1 hour. Okay, I'm going to plug these values into my formula. So big C is what I'm figuring out, is 12 times 1 times 8 divided by 1,000. And when I divide that, 12 times 8 is 96, divided by 1,000, I get 0.096, and that is in cents. Now the weird thing is that this can be rounded And if we round it, the 6 bumps the 9 up to a 10, so we could say 0.10 cents. And I know that kind of looks like 10 cents, but it's actually not 10 cents. This is not the same as 10 cents, which is 0.10 in dollars. Okay, but if we have 0.10 in cents, then that's less than a penny. That's 1/10 of a cent. So that's a very tiny amount of electricity, or of charge for electricity, which is probably why if you go to LCC campus, there's no charge for charging your phone. You can just plug your charger into an outlet on campus and there's no concern about that. The next example could potentially be a little bit more. I forgot and left my heater on all night, 9 hours. The heater is a 1500 watt unit and electricity is 8 cents per kilowatt hour. How much money will this add to my bill? What I realized was that my home heater, although it is a 1500 watt unit, cycles on and off as it reaches a certain temperature. So it probably would not have been running at 1500 watts all 9 hours. But we will run the calculation like that and see what the charge would be if it did run all night. You should try to do this yourself and see what you come up with. The thing that I find most confusing about these two problems is the fact that our answer comes out in cents. But maybe you can figure this one out. It should be a little bit more. Okay, so the big total cost will be 1500 times 9 times 8 divided by 1000. And the order in which I would do this is multiply all the top numbers together first and then divide by 1000. When I do that, I come up with the number 108. That answer is in cents. If you're being charged 108 cents, we could say that that is $1.08. So we can convert that to dollars. So $1 doesn't seem so bad on your electric bill, does it? I guess if you did this many nights over the course of a month, then you could see a significant increase in your electric bill. Okay, we have one more example on this page, and I'm just going to show you the answer key for this. But before I do that, the interquartile range, which is a single quantity, and the first quartile can be used to find the lower fence for a set of data. If this doesn't mean anything to you, I understand. These are statistics terms. What we're trying to show you is that you can use this formula even if you have no idea what these quantities are. And then the other thing is I wanted to point out that IQR isn't 3 different things. It's the interquartile range. That's why I said which is a single quantity. So lower fence equals first quartile minus 1.5 times IQR. Identify the quantities in this formula and which letter is used for each quantity. So here LF is lower fence, Q is first quartile, and IQR is interquartile range. Okay, what would the lower fence be for a set of data if the first quartile is 12 gigatons and the interquartile range is 5 gigatons? So we've written down these two values here, and then we're going to insert them into the formula that we were given. LF is equal to Q, which is 12, minus 1.5 times IQR, which is 5. So in the order of operations, we multiply first and then we subtract. So we're going to have 12 minus 7.5. And that is how we get 4.5 gigatons for our lower fence.